Swayam Prabha. Digital India. Educated India.
So welcome back. So in the before the lunch, Professor Ramu discussed about the big picture of visualization and why it is needed, and then he introduced the self-organizing map for high dimension visualization by highlighting that visualizing high dimension is very important. Now we have come through the multi-objective optimization where there is a Pareto front, and we know that the objectives can scale up to more than 3 objectives as well. So the problems that has more than 3 objectives, it becomes very essential to visualize them. And what I'm going to do, I'm going to present how we have utilized the idea of self-organizing map to visualize the high objective functions and make few decisions. So there are multiple decision making techniques. Pareto race is one of them that I will be focusing for today's talk, and then I will just provide the how it is implemented, and if time permits I will just demonstrate a MATLAB based application that works on the idea of self-organizing map that is integrated with Pareto race. Okay, so this background I think I don't need because we have discussed a lot about generating the Pareto optimal front given the multi-objective optimization problem. So the part that I will be focusing on is to pick one or few solutions out of this Pareto optimal front. And there are multiple ways we can pick one solution out of this particular Pareto optimal front. One could be the reference point, the rough case provided by the decision maker. For example, this point. Given this point, we can find out one solution which is this red color point, which is very close to this particular criteria or the preference given by decision maker. Other could be reference direction. They have some direction. They want some relation between the objective function values, and they have given one direction in terms of weights. So in that particular direction, starting from A, we can find one point over here. So there are such more techniques. For example, classification. Decision maker says that I don't like any F1 values that is more than this particular B. So they don't like any solution that is above this value. They want their F2 to be less than B. So they only like these solutions. And there could be aspiration level, which is this one. Though it is not non-attainable, it's not possible to find any of the solution below this front, but they have given this preference because they don't know how the Pareto front looks. So the idea is to given this aspiration level, how to find the closest Pareto optimal front. So these are the few techniques or the few ideas that decision maker can give to the optimizer, and optimizer can provide you one or few solution on the Pareto optimal front. So there are a lot of interactive MCDM techniques that involves 3 things. The first one is the optimization. The second thing is the preference from the decision maker, and third one is the visualization. Here visualization becomes very important because that gives the overall picture about the conflictiveness or the interaction between the variables. So on the basis of that, lot of interactive MCDM techniques has been developed. So in today's presentation, I will just show how the Pareto race works. So this is the overall idea of the MCDM technique. We will be having multiple objective functions. Given those functions, the decision maker will be having the preferences. If I take the example of a car design, they might want to look into 3 different criteria. One could be safety, speed and cost. And it will depend upon the decision maker. If I consider the military vehicle, maybe for them safety is more important than anything. Maybe speed they are not much interested. If a decision maker comes from the car racing side, car racing company, they will be more interested on the speed and safety. They want to spend more on the cost. They want to compromise. Or maybe for commercial vehicle, cost is more important. Okay, so given the objective, the preferences, when there are multiple solutions, we also need to compare them, how they look like, so that the decision maker can make proper decision. They can compare it properly. So this is the overview of the multi-criteria decision making approach. Now, comparing the objective function is one thing, but the other thing is how to know that how good the solutions are. For example, in the in the group decision making task that is given to you, maybe one of the group decided to reduce the waiting time, correct? But what if in between you go and you are late, you might miss your flight, correct? So the point is that only choosing best solution is not the final thing. We also have to look what are the quality of the solutions. Am I going to achieve that or not? For example, if I discuss about the proximity to the constraint, that means I gave you very good solution, but it is very close to constraint. Would you pick? Designer may not want to pick it because any small deviation from there, it might lead to failure in the design. Next one is the trade-off values. So usually the designer go with very high trade-off values. Robustness is the other thing that Professor Deb discussed about. So we want our objective to be very less sensitive when there is a change in the variable, because suppose I have the current operating condition. For example, I take the case of fan. If a small change in the voltage and the speed of the fan is changing too much, that is not a very good solution, correct? What I want across a band of the voltage, I want my fan to run with constant speed. So we want robust solutions, and there are such other properties. So the idea that I want to give you that only looking into the objective function values are not enough. We have to look qualitatively how good they are. And this is one of the research gap that has been addressed in my thesis. So now when I consider this quality as well along with the objective function, my dimension increases. I have 3 objective and 2 quality. Now the dimension becomes 5. Now I have to visualize the 5 different dimensions, and here ISOM comes for the rescue. So now I will discuss about the Pareto race, which is one of the MCDM techniques, and the idea goes like that. So it is the analogy comes from driving a vehicle on the road. So how driver drives, it will take some direction, it will increase or decrease the speed. So the idea is the designer is trying to navigate on the Pareto optimal front by changing the direction and the speed. So the overall view goes like that. There is a multi-objective optimization problem, and there is a decision maker, of course, and they have to pick a start point. So start point will be one of the feasible point in the design space. Corresponding to that, we will compute the objective function value and calculate the corresponding Pareto optimal solution. So this is the start point over here. Now from here, the decision maker has to make 2 decisions. The first one, in which direction they want to move, and what is the step size they want to move, depending upon the F1, F2, F3 they like. For example, if I take this particular point, it has very low F1 value, very high F2 value, and very low F3 value. Maybe the decision maker wants, okay, I don't like F2 value, I want to change this F2 value. So they can give some direction like this. So when they will move in this particular direction, F2 value starts improving. So now it is 1, which is maximum, it will improve. So this is called as a criteria, basically which objective function they want to improve and which objective function they want to compromise. So this is the criteria. So after giving the start point and the criteria, the decision maker give one direction also, in which direction they want to move. Given the direction, they will decide how much they want to change their solution from the current point. If they want to change it a lot, they have to give very large step size, or if they want to change the solution less, they will give a small step size. So basically this is the step size that we are seeing here. And now if they want to move in the same direction, so here you can see there is a discontinuous, so they may want to increase the speed to avoid that particular region. Now they came up to this particular solution, and then maybe decision maker says that, okay, in this direction, the way these objectives are changing, I don't like it, I want to change my criteria. So they change the direction. So by changing the direction, again this is the new direction and this is the step size, and they come up to a new solution. And over the iterations, they will change the step size and direction and come to a point in which now decision maker says that, okay, I'm happy with this solution and I want to pick it up. Or they want to visualize all the solutions, compare them, and then make a decision which solution they want. So this is the overall idea of the Pareto race. So basically decision maker is navigating on the Pareto optimal front by changing the speed and the direction. Okay, let us discuss about the mathematics about it, how we are going to implement it. Okay, so as of now, suppose I know this is the Pareto optimal front, which might not be the actual case, and this is some initial point which is provided by the decision maker Z1. So first they will provide one initial point and one direction, which is this direction. Now given this initial point, we will scalarize our objective function, that is achievement scalarization function, and we will compute the corresponding Pareto optimal front, which is here. Now the decision maker look into this solution and they have to make decision if they are liking the F1 F2 value or not. If they are not liking, suppose, then on this particular direction they can give the next step. Okay, now I want to change my point from here to here with T step. Now given this new point, we will get next solution. Then again they will see how much they are changing. So for example, for F1 they compromised to gain on F2, and up to this point they figured out, okay, I have given wrong direction actually. I wanted to increase my F2, I wanted to gain on my F1. So suddenly they decided to change the direction. So now this is the new direction. Now the good part about this direction is that now they can increase in this way. So slowly on this particular direction, again given the step size, we are getting new solutions. So earlier we were moving in this direction and decision maker decided now to move in this direction, correct? Because they wanted to increase their F2 and get gain on F1, which was not happening in the earlier case. So again in the multiple iterations, by changing the direction and the speed, finally decision maker came here and they said, okay, I'm happy with this particular solution. So there are a few features in the Pareto race that I would like to introduce. One is the, of course, start point, which is here. The other is constant speed. That means the step size is constant every time. I am making this step size constant every time. I am not changing it. The second one is the gear. Gear says like decision maker is increasing the step size. Brakes means they are decreasing the step size. Turn means they are changing the direction. And end point is the final solution. So all the analogy comes from driving a vehicle and the actions that driver can put on the speed or the direction, and that is directly translated to the idea of the Pareto race. Okay, so there are few limitations of the Pareto race, but in interest of time, I am just going to skip it. So, yeah, so there were some issues in the parameters. They were not very well defined. So in our work, we have redefined those parameters and make it customized so that the decision maker can provide those particular parameters in well manner. Okay, so I'll skip this part. Okay, so I discussed about the performance measures. I told only looking into the objective function is not sufficient. I want to know how good the solutions are. Okay, so one is the closeness to constraint. I give very good solution, but any small change in variable may lead to failure. So decision maker will not like that particular solution. Other could be a robustness. If I take the same example of the flight, we will deciding on which flight we have to take. Okay, so what robustness says that, okay, I found a solution which is giving me very less cost, but the problem is that one flight usually get delays, and I know this information. So there is a uncertainty. So what if it delays? Would I still consider that solution or not? So these are the few practical aspects we have to include in the decision making. Okay, so closeness to constraint, robustness, and trade-off among the objective. These are the three performance measures that I have introduced in Pareto race, but it could be other as well. So just recap about the self-organizing map. So it is a type of artificial neural network. So just consider the example of this bowl shape function, and this red color data, they are coming from this particular equation, y is equal to this particular x1 x2. Now the black color nodes that you are seeing here, these are the initial neurons. These are the untrained neurons of self-organizing map. What self-organizing map will do, it will try to capture the trend and the topology of the function. So the weights of these black dots that we are seeing here, okay, the animation is not coming. Okay, that's fine. So what will happen, the weights of this particular black dot, they will dragged into this particular data space over here. So over the time, it will take the shape of bowl function. So the black nodes, it will take the shape of the red color data point, and the corresponding visualization we can see here. If you see your bowl shape function, it has 4 maxima at the corner and 1 minima in the center, and we have clearly captured this thing here. Okay, so in this case, y is the output function, and we are able to capture the trend and the topology of the function. Now what we are going to do, in case of multi-objective optimization, we have multiple functions. Okay, so now we will visualize each of the functions separately, knowing how they are interacting with each other. So if I take the C2 problem, it tells that okay, there are three objective function f1, f2, f3, and if I look into this particular region in between, okay, so this is the trade-off region in which none of the f1, f2, f3 are maxima or minima, they are in intermediate value. If I look into this particular region here f1 is maximum and the corresponding f2, f3 value is minimum, and we can see over here as well. So we see how they are interacting. One objective is maximum and the same way, and at the same location other objectives are minimum. So they are conflicting in nature. So this gives very good idea. So the question comes, okay, f1, f2, f3, I can see the same thing over here. But the good part is that when there is a high number of objective functions, it will be very difficult to visualize in the scatter plot. There we can show how self-organizing map can help a decision maker. Okay, so what we proposed, we will use the self-organizing map for visualizing the Pareto race and its features with few modifications that I skipped. And on the top of that, we are also interested in knowing how good the solutions are in qualitative sense. For example, closeness to constraint, trade-off values, and the robustness. And each of the steps of the Pareto race, we will demonstrate using the color scheme. For example, if any hexagon which is coming in this black color boundary, it will show that there is a disjoint. The boundary of the Pareto front is disjoint. All the start points we will show by the black color. If some solutions are close to constraint, we will show in the gray face color. Then accelerator we will show in the green color. So this color scheme is given so that the decision maker can identify, okay, which action the decision maker took, where it changed the direction, where it changed the speed, where it decrease or increase, and also the final solution by red color. So we'll take a few examples and demonstrate how this is working. Okay. So let us take the same example, C2 DTLD2 example, and you see the U matrix. These high values that you are seeing here, this is the clear indication that there is a cluster. Okay, and we can see there are 4 different clusters. So this gives, okay, there is a disjoint region in the Pareto front, and all the cells in the black color, it is indicating that this part is discontinuous. So all the cells, all the hexagons that is in black color boundary, it is the indicator that there is a gap in the Pareto front. Okay. Now this gray color, that cells you are seeing here in all the plots, that says the corresponding solutions are very close to the constraint boundary. And of course you can see the interaction between f1, f2, f3. Okay. Now let us introduce the quality matrix and see how the decision making could happen. If I see the G, which is closeness to constraint, it is clearly telling that these regions which is in yellow color, these are really very close to constraint, and decision makers may want to avoid such kind of solutions. So in this example, for example, decision maker starts from this particular point and it realizes that, okay, I have good f1 value, good f3 value, f2 is not so good, but it is very close to constraint. And they immediately wanted to move from that particular region because those are very critical solution. The other thing is, if I see the trade-off value, at the initial point trade-off value is very less, and there is a region where trade-off value can be very high. By knowing these two information, which is G and T, the decision maker may want to move in this particular region in the hope that I will get very good trade-off value, okay, and I will move away from the constraint. These are the two good news, but at the cost of f1. I have to compromise on the f1, but I will get very good trade-off solution and I will move away from the constraint boundary. So slowly you can see it started from this particular point and in the progressive direction by changing the direction and speed, and it picked this particular point. Now they are well aware of the solution they have picked. They know that, okay, I am compromising on f1, but my solution is very reliable. It is away from the constraint and I have very good trade-off. So this is one example. The other one is the benchmark example in which there are 3 objective function f1, f2, f3, and you can see the component plane of f1, f2, f3. So it clearly says that f1 and f3, they are conflicting with each other. So here f3 is very high and here corresponding f1 is low. So if you want to improve on F3, you want to come over here, you have to sacrifice on F1. Okay. The other thing, F2 is also conflicting with F3 because F2 has very high value here and F2 has relatively moderate value over here. So the conflictiveness of the objective function is very clear here. And suppose the decision maker is start from this particular point, which is the black color node. Okay, let us analyze what are the properties of this start point. It has relatively lower value of F1, lower value of F2 and higher value of F3. Okay. If I look into the closeness to constraint, it is relatively close to constraint and trade-off value is moderate. So again, in this case, decision maker want to move away from the constraint by improving F3, F2 and sacrificing on F1 and keeping the trade-off value almost the same. So slowly they moved in this direction and picked this particular solution. Okay, so this is the last example that I would like to show. In this case, there are 5 different objectives. And this is the multiple clutch brake design problem. The 5 objectives are mass, minimum stopping time, RPM, outer radius, force. So these are the 5 objectives. Let us analyze how they are interacting. If I look into mass and minimum stopping time, they are conflicting with each other. If my mass is high, the minimum stopping time will be less because of inertia. And similarly, we can see other objective conflictiveness behavior as well. So these are the 3 quality indicators, which is closeness to constraint, trade-off and robustness. Okay. Let us assume that designer starts from this particular black color point over here. If I look the same black color point in G, okay. So again, it is close to constraint. It has very poor trade-off value. Okay. And also robustness is not that good. So over the time they wanted to move out of this particular place. So quickly they moved here by very high step size and they started moving in the same direction. But what they realized, okay, now they are going in the wrong direction. They wanted to come here. Okay, they wanted to come at very high trade-off value. So they changed the direction. So from here to here they have changed the direction and slowly they came up to a final solution, which is here, which is very far from the constraint boundary. It has very good trade-off value and moderately good robustness as well. And yeah, this is the 10 objective function, which again uses the concept of Pareto race by changing the speed and direction. So I'm not going to explain this. And yeah, so in summary, we discussed about the isom visualization method and how it is useful in high dimension, specifically in the case of multi-objective optimization where we have multiple objectives, and we have seen how it helped in the case of Pareto race by giving the crucial information to the decision maker, not only the interaction between the objective but also the quality of the solutions. I presented Pareto race and you have seen multiple components, especially the optimization, decision making, visualization, and that really needs a one platform because it requires to and fro information. So it requires one unified platform in which all the 3 tasks can happen simultaneously. So I'll quickly take one example and I will demonstrate how the decision making can be happened on this kind of platform using Pareto race. Okay. So let us take, we have 2 variables. So here we can define 2 variables, x1, x2. You can see we can give the upper bound and lower bound and we can add it. Then the second variable, add it. And let us take the 3 objectives. We'll quickly take F1 as x2 and we can add it here. Then maybe this is F2. So the second objective function is x1 minus x2. So it is added. Then let us take the third objective function. Okay. Okay, so I have defined 3 objective functions. Let us say there is no constraint and we are giving the population size of 500 and we will run it for maybe shorter generation. And here we click and we get the Pareto front. Okay, it will take some time. Okay, now the Pareto front came here, you can see. Okay, now this says that the optimization is completed, and we get the Pareto optimal front, the optimal design variable values, and the corresponding isom plot. Now this, by looking into these three plots, the decision maker has very good idea about, they have very good idea about the interaction between the objective functions. Let us quickly take the case of Pareto race, in which I'll give some start point, maybe the middle region over here, and let us take 1, then minus 0.5, and maybe 0.75. So these are the start point. Given this start point, we will get one solution on the Pareto optimal front. So for this criteria given by decision maker, now we have one solution. Now from there the decision making will happen. By looking into that, the decision maker suppose decided they want to reduce the value of F3, okay. So preferences can be given here. So if they want to reduce the value of F3, they have to sacrifice on F1 and F2. So of course F1, F2 they want to increase. So I have given this greater than sign here. F2 they want to increase, and F3 they want to decrease. So now this gives the information about the direction, which direction they want to move, and then they can pick the step size, how much they want to move from the start point. So you see, from the start point they got the new solution over here, and again they can do this thing in iteratively, and they get new point here, then again new point here. If they want to change the criteria, they can just go pick one objective and change any of the criteria, and again they can compute new solution. Okay, see, now the direction has been changed here. So this is clearly showing how the preferences of the designer is changing, and also the solutions are changing on the isom plot. Next, what we can do, only for these MCDM solutions or the red color solutions, we can go and see how they are interacting with each other. Okay, so that comes in this plot. So the blue color bars, these correspond to objective function 1, the red color bar is F2, and the yellow is F3, and you see over the iterations, the first solution, which is this red, second, third, fourth, how the objective function is changing. So basically F1 is increasing, F2 is also increasing, and you see F3 is decreasing, and that's what the criteria we have given. Okay, so yeah, these are the interactive methods that we can use, and it's very imperative to think in that direction, that we should have a unified platform in which all the optimization, decision making and visualization can happen simultaneously.